Hi there. I thought I would try to record a video about this interbeam scattering work I'm doing. Okay, share my screen. All right, so the context, let me first say that this was work that I did in my PhD thesis, which I finished in 2006, an analytic approach to eigenemittance in storage rings at Stanford, and my PhD advisor was Alex Chow. I worked at Slack, and I kind of did two different projects, one about interbeam scattering and one about perturbation theory near resonances. But I'm going to focus on the interbeam scattering part. So this is my thesis, and most of this is in there, but more recently there's been interest in spin polarization. I'm on a weekly meeting with a number of folks, including this guy Des Barber, who has dedicated his life to high energy spin dynamics, and he did a lot of work on Hera. He's in Hamburg. Anyway, so I think 15 years ago he asked me to apply my interbeam scattering work to spin depolarization, and I told him I would, and I never got around to it. And because basically I calculated the moment evolution and not just the diffusion coefficient, which sounds, I didn't think should be hard, and somehow I could just never get myself to do it, and now I'm trying to do it. And it's not so hard, but there's just so many steps in this whole process. So this is another write-up I'm working on with another Dan Abel, who lives near me, and we are doing this this work here. Okay, so I am putting a keynote presentation together. Anyway, I'm trying. So one way of starting this is to say that you have an equation of motion for the particles in phase space that has a Hamiltonian part and then a fluctuating part, and you could say this is a stochastic differential equation. Let me just quickly talk about the spin context. Basically, this would be something like in the this would be the Electron Ion Collider and the electron beam, and you want them to be polarized for the collisions with the electrons and the protons, and probing the small scale structure of the protons. And there's something called the invariant spin field, which means the particle in phase space has a certain spin, and it goes around one time and arrives at a different place, and the spin is evolved also, and so you want the spin to be such that the spins don't change as the orbital motion occurs. But if you set up your particles according to this invariant spin field, but then you add a diffusion process, then that's going to mess things up a little bit. If you get a little kick, then the spin's going to be a little bit off, and that's going to mean that you're not on the invariant spin field, and which gives you the maximum polarization, so you've decreased your polarization. And for the case of synchrotron radiation, there's something called the Durbanev-Kondrachenko formula that tells you how much depolarization you're going to get. And there's also the SLIM formalism, which my advisor Alex Chow did, and that's similar. It's maybe slightly simplified, but it's a nice, clear formulation of this. So anyway, what I want to do now is figure out how interbeam scattering fits into that, so if I can compute the diffusion coefficient. So here I was kind of reminding myself and maybe writing it out a little more clearly where the diffusion coefficient comes from. So you've got this stochastic differential equation, and you can write down a corresponding master equation, which says that the change in the distribution in a time delta t, or df dt, is given by the total number of particles scattering in and minus the number scattering out. And then you've got some process W that's a probability distribution. It gives you the probability of, it's the stochastic process and has associated probability of scattering by delta z in a time delta t. Now, if you assume that delta z is small and you do a Taylor expansion, then you get this first term with basically the f of z term goes away, and you get these two terms. If you expand to second order, you get the delta zi, you get the delta zi, delta zj, and then those are integrated over w with w and over delta z with w, and then this gives you the Fokker-Planck equation with these definitions of the drift and diffusion coefficient. There's another way of deriving it in terms of the moments, which I won't talk about. Okay, so you can now assume that actually within this time delta t there are n kicks, and so you break up the total kick into the sum of little delta zi super j with from 1 to n, where these are n kicks, and then if you do that, then and you expand out the diffusion coefficient, you find there's terms that occur at the same time and terms that occur at different times, and when you do the averaging, you assume the terms that occur at different times are going to go away, are going to average to 0, so you get rid of that, and then you get these expressions here with the n dot. Wait, did I leave out the n dot? Anyway, you get these expressions here down at the bottom for the drift and the diffusion with the extra n dot. And here G is basically the same as W. I've been trying to think about notation and how do you talk about stochastic processes. You have a process W and an associated probability distribution G, depending on some parameter phi. But basically G and W are the same thing. And so the delta Z is the kick depending on this parameter phi. And we get this integral, and you have this n dot is the event rate. I know this is probably too fast and I need to go over this more slowly, but I'm trying to get through this. So you also need to be careful about transforming into the beam frame. Possibility I've still made a mistake here, but I'm trying to, anyway, for the longitudinal one, you get this gamma cubed here. This is the transformation of the phase space variable. So now here we go to calculate all these quantities. You want to calculate this. So the parameter phi, the scatter, you have these two particles sitting in phase space. You focus on one and you ask, well, what happens as they scatter, and you calculate a time t min until they reach their minimum, the minimum approach, and you can so delta is defined. This is not sure this is self-contained, but anyway, you calculate this time minimum approach, and you say, let's just consider those scatters that happen within when t min is less than the delta t that you fixed. So then that specifies your probability distribution. It's just the probability distribution of the other particle, but you have to reduce the phase space given this condition of hitting delta t min within delta t, and then you can another calculation is to do this, calculate delta P1, the change in the momentum particle 1 in this time period. And so then you get these expressions. So we're still, this is the expression for the drift and diffusion coefficient, which turn into these after applying a couple additional conditions that I talk about in the thesis. There's a reversibility condition and such. So these are the expressions for drift and diffusion we've got. It's a 6-dimensional integral. Now, if you assume that the distribution breaks into a product of, I should say that in the thesis, I took this expression and then calculated the moment evolution, which gives you the same result as if under certain approximations, you get Bjork and Matingwa and Pavinsky are the standard results here. But here I want to go in this different direction and just directly compute the diffusion coefficient. And so if you make this assumption that the distribution separates into a product of position and momentum, and then you do the position integral, you get this g because you've sort of switched variables a little bit, and then if you say the g is constant, then that integral turns into, that gives you the Coulomb log. And so that shows up as the Coulomb log, and you get this expression. I think I left off the number of particles. There's an n overall here. And this is, and there's oh no, that's right. Anyway, this is equivalent to the Rosenbluth potentials or the Landau collision integral. So this isn't too bad of a equation. It's just a 3-dimensional one. Rho p here is the particle distribution of the in momentum space. And so you can go ahead and explicitly write down what that integral is, and see it's a 2-dimensional integral now, and you can do one of the integrals, the delta integral, but then you still have 2-dimensional integrals left. And now in the case that basically this is kind of the equilibrium case, where the temperatures are the same. So if you take that case, then you can pretty easily do this integral and get a result. So anyway, I've got this result. I think I might still have a factor off. It's a little strange that there's no gammas left at the end. So still working with this to make sure I didn't make some mistakes. And then I'm comparing this with the synchrotron radiation calculation. So that's sort of where this problem is at. I know it's a lot, but I don't quite know who would watch this. So I thought it would be helpful to try to record myself talking about this. So if there's interest, or just if I feel it's helpful for myself, I may try to record a few more videos going into more detail and giving further summaries of this work. But that's where things are at with intrabeam scattering and spin depolarization. Thank you for listening.